We are continuing our examples for hypothesis testing using the goodness of fit test. These examples are in OpenStax Introductory Statistics textbook, and in our notes we are now going to discuss a situation about a study that indicates that the number of televisions that American families have is distributed as in the table below. The table indicates that 10% of American families have no televisions at home, 16% of families have one television, 55% of families have two TVs, 11% of American families have three TVs, and 8% of American families have 4 or more TVs at home. A random sample of 600 families in the far western United States resulted in the data shown in the table below. 66 of those families had no TVs, 119 had one TV, 340 of the 600 families had two TVs, 60 of the 600 families had three TVs, and 15 had 4 or more TVs. Our work is at the 1% significant level to determine if it appears that the distribution number of televisions of far western United States families is different from the distribution of the American population as a whole. So when we are trying to do this hypothesis test, we need to understand what is the null hypothesis and what is the alternative hypothesis. The alternative hypothesis will be whether the distribution of the number of televisions of far western United States families is different from the distribution of the American population. This is our task. So therefore, the null hypothesis will be that the number of TVs distribution for far western United States families actually follows that of the US families. Arithmetically or numerically, that means the proportion of families with 0 TVs is 10%, the proportion of families with 1 TV is 16%, the proportion of families with 2 TVs is 55%, the proportion of families with 3 TVs is 11%, and the proportion of families with 4+ TVs is 8%. The alternative hypothesis will be that the number of TVs distribution for far western US families is different from the distribution of all the US families. And we have a significance level of 1%, and we have 5 categories, 0, 1, 2, 3, or 4+ TVs, and therefore degrees of freedom will equal 5 minus 1, or 4. To do the test manually, we need to find the Pearson residuals and add them up to find our chi-squared. So we need the expected number of counts for families in far western United States if they were following the null hypothesis, which is a distribution of all the US families, and that will be 10% of the 600, 16% of the 600, 55% of the 600, 11% of the 600, and 8% of the 600. And the counts would have added again to 600, but they will be following the theoretical distribution with the proportions indicated in the first table. After that, we need to find the differences observed minus expected, square those differences, and divide by expected to find the Pearson residuals. So when we do that, we can add the Pearson residuals that we found them to be 0.6, 5.51, 0.30, 0.55, and 22.69, and that will give us our chi-squared test statistic of 29.65. After that, we want to go and use some kind of technology to find the area to the right tail of a chi-square distribution with degrees of freedom equal to 4 and a test statistic value of the variable of an chi-squared score of 29.65. So I'm going to go to Art of Stat, chi-square distribution. find probability, and I will include 4 degrees of freedom, probability in the upper tail, value of x to be 29.65, and you can see that this graph does not show the value of 29.65. Actually, this graph completes the chi-square distribution with 4 degrees of freedom at a value of chi-squared of 18. 29.65 is very far to the right, and the area under the tail is approximately 0%. So this p-value is much smaller than alpha. It indicates that it is a very unlikely situation that this particular sample of 600 families could have come from a distribution of TVs that agrees with the whole US American population, and therefore we can now reject the null hypothesis. Our conclusion is that at the 1% significance level, the sample data provide enough evidence or sufficient evidence to support the alternative hypothesis that the number of TVs distribution for far western US families is different from the distribution of all the American population. So remember again, in your decision, you want to either reject the null or fail to reject the null, and in your conclusion, you want to support the alternative or fail to support the alternative hypothesis. Again, without technology, this is not possible to happen. So we want to use technology to do all of these calculations. We really do not want to do them by hand. One option is to use Excel. We have already coded our processes here with a previous example. So we just want to copy down and update. We have a new variable. The variable is number of TVs in far western United States households. So number of TVs in far western US households, and the values are 0, 1, 2, 3, or 4 plus. I don't know if it's gonna take it. Yep, it did. All right. And we had collected sample data for 66. Let me see here. 119, 340, 60, and 15. And we had different, it was not a uniform distribution this time. We had a theoretical distribution of 10%, 0.10, and 16%, and 55%, and 11%, and 8%. And this gave us expected numbers. Remember, theoretical numbers don't have to be whole numbers. They can be decimals. And so here I have a problem. Do you see the problem? The problem is that the total of expected numbers happens to be 60. This is because when I coded here, I asked for the column E and the cell 12 to be a static cell, but I want this time to be column E and the total of my new observed frequency, so I have to fix that. This is row 35 and it is not 12. So I want the expected values to add up to be 600. So I want to copy the new formula. Make sure you do these updates. Double check that you have a total of observed frequencies and expected frequencies to be the same. And now I do have reasonable values like the ones that I found manually in my notes, and a test statistic that matches what I found in my notes. It is 29.65 if rounded to the nearest hundredth. I have 4 degrees of freedom. I have a p-value of 0.000006, and that is because this value of 5.77 written in scientific notation has 5 located 6 places to the right of the decimal point, and I had an alpha of 0.01. I want to update that, and I see that this p-value of 6 times 10 to the negative 6 is much smaller than the 1% of alpha, and that will result in rejecting the null hypothesis. Let's update our null hypothesis and our alternative hypothesis to agree with the story. So our null hypothesis is that the number of TVs in far western US households follows the distribution of TVs in American households, the theoretical probabilities, and that the alternative hypothesis will be that the number of TVs does not follow that of the American households, and therefore, with a p-value indicating a very unusual sample coming from the theoretical distribution, I have enough evidence to reject the null hypothesis, and at the 1% significance level to support the claim that the number of TVs in far western US households does not follow the distribution of TVs in American households. As a reminder, another way of doing this goodness of fit test is to actually use the Art of Stat app for the chi-square test. Select the goodness of fit. Enter a contingency table with 5 categories. Category 1 will be 0 TVs. Category 2 would be 1 TV. Category 3 will be 2 TVs. Category 4 will be 3 TVs. And category 5 will be 4 plus TVs. I had the counts of 66, 119, 340, 60, and 15. And I had the probabilities of 10%, 16%, 55%, 11%, and 8%. Remember to write 8 as 0.08 and not 0.8, and let's submit. Make sure we have correct counts. So the observed counts add to 600 and my hypothesized proportions add to 100%. Excellent. The expected counts are shown, the residuals are shown. The null hypothesis as a mathematical expression for the proportion in each category is shown. The test statistic is the one that I actually calculated in Excel and manually of 29.65, and the p-value is much smaller than 0.0001. So it shows here with accuracy at 4 decimal places of being 0. This p-value is much smaller than our significance level of 1%, and therefore we have enough evidence to reject the null hypothesis and to support the alternative hypothesis.